efficient markets hypothesis. So the idea behind this was that it goes back to 18 or 1700s with Adam Smith, and the idea was that somehow you had stock prices oscillating around a true value. Okay? And so a lot of effort went into finding the idea of what is the true value of that stock. And then you could buy ones which are relatively cheap as opposed to those that are overpriced, which you could then sell. And essentially it came after a lot of effort. If they worked out that, well, that wasn't really what was going on. So then, or they thought that might not be what was going on, so economists came up with the idea of an efficient market hypothesis. And that's basically saying that somehow the prices themselves incorporate all the information. So rather than there being a true price, the price is the true price, and somehow we have to understand what that true price is and how it gets to there. So the various forms that they came up with was a strong form, which says that the market prices incorporate all the information, both publicly and also those that are only available to insiders. So that would be true if, for example, you were somehow magically the board of directors who weren't talking publicly, their consciousness got into the share price somehow. The semi-strong form basically says that it incorporates all publicly available information, but not the private stuff. And the weak form basically says, well, it's basically just statistics, and the market price incorporates all information in the price history. So those are the three forms. A lot of effort went into working out whether the strong form exists or the weak form exists, or whether it's the semi-strong form. To test the strong form, there's a logical problem there, because by definition you are assuming that there's information in the prices that you are not available to get hold of, okay, because it's private. So logically that's a bit of a problem. Okay, so people have tried looking at directed share dealings, assuming that was it, but of course, as we see, or said before, directors may deliberately support their price of they may react counterintuitively in order to defend the stock price, even if things are going bad. Testing the weak form using price history, there's really, the studies have failed to identify any difference between on returns using technical analysis and those which are just random selection. So essentially, although there's no positive strength, there's no positive support for the weak form, there's no real positive reason not to believe that it's true. So it's all a bit of economic theory. There are information efficiency tests that you can look at, volatility tests that you can read about, but the conclusion is that essentially no one knows what's going on. Okay? So these are probably very important to economists, but in reality they're theoretical ideas, and you could argue whether they've actually taught anybody anything that's useful. Right, okay, so now we'll move on to random walks. So this is now moving on to the preliminary material that we'll need to lead up to when we're coming up into pricing options and using martingales and things like that later on. So I know that some of you have done stochastics before, but I'm just going to run through briefly here the bits that we'll need for later on. So a couple of definitions to start off with. First thing is a deterministic system. So a deterministic system, for want of a better description, is a clockwork system. Okay, it's perfectly described. I wind up the clockwork toy, and then it carries on in a predictable way. I can write down the equations that will, in theory, tell me what the state of the clockwork toy will be in a year's time or something like that. That's fine, and I can, providing I've got a perfect computer that hasn't got any numerical truncation errors, I can run that computer and I will be able to predict the state of the clockwork toy, or the state of the system, or the state of, if you believe the universe is deterministic, the state of the universe in a year's time. The problem is, though, that in order to perfectly describe a deterministic system, even if you believe that the state of the universe is fine, is correct, is deterministic, then what you've got to do is you've got to describe every possible interaction between every possible particle in the universe. And in order to do that, you're going to need a computer bigger than the size of the universe to do it. So it's not perhaps a credible thing to be able to do. So to that end, you then move towards a stochastic system. And essentially a stochastic system models the key features that are going on, but ignores, or rather it lumps all the other complex interactions that are going on in the world into a random term that's drawn from a particular distribution, statistical distribution. And the idea there is to say, well, life is really complicated. Say, take stock prices. If we could model the interactions of every possible particle in the universe, theoretically we'd be able to model the prices of stocks as they go forward, because we'd know how people were interacting, we'd know how everyone in the world was thinking in order to do things, and that isn't really going to be feasible. So because stock prices are obviously they go up and down quite in an unpredictable, relatively unpredictable way, we move to the point where we say, well, we're going to say that the stochastic system is perhaps a better model for this, because we can say that the unexpected movements or the pseudo-random movements of the stock prices can be modeled by random numbers drawn from the distribution. So the thing here, though, is when you have a stochastic system, what you often do is you write down a stochastic differential equation, and it consists of a small jump dx. X is the quantity you're interested in, and you consider the jump over a time step dt, an infinitesimal time step dt, and the jump in dx is, for example, you might write down the stochastic differential equation, dx is mu dt plus sigma dbt. So what does that mean? That means that the change in x is could be this mu could be a function of time, it could be deterministic, it may not be eventually, but it says that there's a small increment in x in time step dt of mu, okay, mu dt. The next bit that you've got there is a sigma dB sub t, and this number is a random number, which is drawn in this case, well, we'll see in a minute, from n naught dt. Okay? That could be any distribution. I'm just going to draw it from the normal distribution. Typically, that's what we'll do later on. But essentially, this is deterministic, so this is predictable, and this is unpredictable. I mean, this is strictly deterministic. The proper maths was deterministic, and this is stochastic. Okay? So what that means is that if I start at a certain time, and I then start incrementing my value of x, I'll start with a value, say, at x0, and then at time step of dt, I'll get to x dt, and then in order to get this, the way that I get from there to there is this dx jump here. So what will I do? I'll start with a known value of x0, I will increment it by mu dt, and then I will also increment it by sigma, and then draw a random number from this normal distribution. And when I do that, I'll get a value of the x dt. And then if I want to go x of 2 dt, I'll do another time step here. The jump in this time step will be, again, mu dt. Mu might be a constant. If it is, it's the same deterministic bit. Then I'll take sigma as a number, and I'll draw another random number from this normal distribution. Completely different random number in general. It's going to be from the random number I drew here. So my time step here, my jump in x here is going to be different, okay, and unpredictable. And I can carry on doing that all the way through. And I will end up getting a series of values of x that then give me a time series in x. Now, let's say I start again. I start again with exactly the same value of x0, and I time step dt again. When I time step dt again, I'll get mu dt. That will be the same as when I started initially at x0 before. I'll do sigma. I'll now draw a random number, but that random number isn't necessarily going to be, or it's almost certainly not going to be the same random number that I drew the first time. So when I do the net, if I reran that time series, I would get a different set of numbers. Okay? So when you solve a deterministic system, as we saw in differential equations, if you did 1052, you solve it, you get the same answer every time you solve the equation. Okay? When you solve a stochastic differential equation, you get a different answer each time you solve the differential equation. Okay? So what does it mean to have a solution of a stochastic differential equation? Well, what it means is, if I say plotted this out against time, and this is x as a function of time, I might start off with my x0 here, and I plot it out, and we'll see later, I might get a time series that does that. If I then go back and start with x0 again, and run the same system again with the same stochastic differential equation, I'll run it, and I'll get a time series like that, completely different answer. And I do it again, and I'll get a time series like this. And you carry on, and you can see that what happens is, if you run the thing an infinite number of times, and generally you'll get an infinitely different set of solutions. But what you'll see is, though, if you take a time slice, say at t0, and you plot the xt, and you bin this, if you like. If you take bins here and you say, well, what's the value of xt, count all up the number of times it crosses through here, you will in general see a distribution. Okay? So you'll see a distribution. So what this means is the solution of a stochastic differential equation isn't a unique value of x. It's a probability that your x value is going to lie within a certain range. So the actual solution of the stochastic differential equation is a probability density function, effectively. Okay? Or you interpret the solution in terms of a probability density function. Okay, so we'll talk about that later on. Let's start off with a just simple random walk to start off with. Okay. In what follows, I'm going to use n mu sigma squared to denote normal distribution with mean mu and variance sigma squared. Okay. Right. So I'm going to consider the random walk Bnt, which is in discrete time t. So I'm going to define Bn of t to start off at 0. Okay, so Bn of t, I'm going to have Bn of 0 equals 0. I'm going to have spacing between time steps is 1 on n. I'm going to have an up-down jumps is going to be 1 on root n. Okay, and the probability of up or down is equal to half. So basically what I've got is, from time step, in a time step dt is 1 on n, I've got Bn of t will go to Bn of t plus 1 on root n to Bn of t minus 1 over root n. Okay? Now, if I do this in time steps, if I discretize everything, so I've got time is discretized as I over n. Okay, I'm going to have n time steps, I equals 1, 2, or 0, 1, 2, 3. Okay, then dot, dot, dot. Then, in general, what am I going to be able to say? I'm going to be able to say that the formula for the Bn at the time step I over n is the value of your Bn at the previous time step plus a number xi divided by the square root of n, where xi is plus or minus 1 with probability a half. Okay, so that's the recurrence relation, or the generating function that I'm going to have to generate that random walk. So you see, essentially what I do is I start at 0, I take a coin and I toss it, and if it comes up heads, which it did, I go up 1, next time step, toss it, comes up heads again, I go up again. Next time step, toss it, comes up tails, I go down. Okay? So you just keep tossing the coin each time and you go up, up, or down, down. Okay? So if you then look at that, and you do it for different values of n. So here is n equals 32. This is just one simulation that I did. If you did the same simulation, it would work differently. So n is 32, I get that. Sometimes I go up 3 or 4 steps, come down 3 steps, up 1, down 1, and what have you. Remember that n determines the size of the jump as well as the time step. So the larger the value of n, the smaller my jump and the smaller my time step. So I'm just going to ramp up n from 32, 64, and you can see in general I'm going to get a different random walk each time. Even if I kept n the same and reran it, I would get a different random walk. What I just want you to look at is just to look at the types of curves that we're getting. N is 128, n is 256, 512, 1024. So, by the time you get to, say, 512 or 1024, if you compare that with things that you see on Bloomberg or something like that, for stock prices, they look similar in that they are jagged, there's a fine structure to it, it's going up and down in a relatively unpredictable way, and so in that sense, you might think that this might be a good model for playing around with simulating some stock prices. Okay? So what we want to do is we want to see what that might lead to if, for example, we let n go off to infinity. So remember, if n goes to infinity, you're in this weird situation that the time steps go to 0, which isn't so bad from a calculus point of view, but so do your jumps. So what's going to happen? Okay? Well, the answer is you still get jumps. It's infinitely small, and you still get this is a non-differentiable curve, okay, in the limit as n goes to infinity. So, what then, in the limit as n goes to infinity, what can we say about that random walk? We've seen that if I put different values of n, it obviously looks more on a finer scale structure. If I rerun it several times, I'm going to get different answers out. So, what am I going to do? Well, let's look at some statistical properties of that random walk. So, I'm going to take the distribution at time t equals 1, and by induction, I'm going to have n plus 1 possible values. Why? Because each time I go up, I've got 1 on root n, and so I've got n steps there, so I'm going to have n plus 1 possible different values. That's not quite right, is it? Yeah. Yeah, okay. Well, anyway, they will range from minus root n to plus root n. Why? Well, the worst, I'm going to be at plus root n if I have an n time steps. I always go up. So n times 1 on root n is going to give me plus root n. If in the unlikely event that in n time steps I always go down, I'm going to end up as minus root n because I'm going to have n lots of minus 1 over root n jumps. So the actual value of t equals 1 is just formally given by the sum of all those xi's over root n, and xi's are independently distributed random variables, plus or minus 1 with probability of half each time. And so the mean value of xi, if we work that out, is plus 1 times a half, minus 1 times a half is 0. So the mean value of the xi's are going to be 0. The variances of the xi's, if we work it out, look, a discrete distribution, take the plus 1 from 0, minus 1 from 0, square it and multiply by the relative probabilities and add, and you get 1. So sigma squared, the variance of that is 1. Okay. So now then we look at if we look at the handout that we had, those are we're adding up there random variables, independent random variables. Each time we add an xi on there, we're adding them up. So the mean and sum of the n independent xi's, the mean of the sum, is also going to be 0. Why? Because each of the means is 0, so then the sums of the means are going to be 0. And the variances also add up. they are n lots of 1, so the variance of the sum of the xi's is going to be 1. So the mean of the distribution of Bn of 1, if we ran it an infinite number of times, would be 0, and the variance is now overall just 1. Sorry, n. Bn of 1. Oh, no, but then we've got to take into account 1 on root n, sorry. So then the variance turns out to be 1. Right, okay. So this is actually essentially a binomial random walk, and in the limit as n goes to infinity, the distribution of that random walk becomes n log 1. Okay? So in the limit as n goes to infinity here, okay, this becomes Bn of t becomes drawn from n log of 1. Sorry, Bn of 1. Okay? So it's like saying, rather than going through all the time steps of doing the up and down and tossing the coin each time, as n goes to infinity, you can just say, well, at time t equals 1, let me just draw a number from an n naught 1 distribution, and that will be a simulation of effectively the endpoint of the simulation of that random walk. If you did that lots of times, or if you did the random walks lots of times, conversely, it would tend towards a normal distribution at time t equals 1. So if this was t equals 1, okay, then this would be x t0. This would be t equals 1, t equals 1. And this would be then an n naught 1 distribution around 0 with mean 1. Okay, so how does it work then for general t? Okay, for general t, you can do it by a little bit of fiddling here. Essentially, t is n lots, or you sum from I equals 1 to nt in discrete time. You then multiply the number of finite time steps in order to get to time t rather than just to time 1. The binomial walk, the endpoint is still the sum over all the xi's divided by the root n, but now you play the trick of you multiply top and bottom by the square root of n, and then effectively by a rescaling, you've got a root t times your original Bn of 1. Okay, all you've done is you discretize on a much finer scale there, but you've still got Bn of 1. And essentially you can see that the Bn of 1, Bn of t, is root t times Bn of 1 effectively, or is drawn like that. So this is drawn then from n naught t. Okay, so the Bn of t in general is going to be drawn from normal distribution with mean 0 and variance t. Okay. So, in the limit as n goes to infinity, what we're saying is that that binomial walk is effectively a random number drawn from a normal distribution. That means that if we walk from time step t to time step t plus dt, we draw a random number from a distribution. What we've got then effectively is, sorry, let me just redraw this. If I do it, say, at t equals 1, okay, and then I do it at a general time step t greater than 1, and a time step t less than 1, then what you've got here is a probability distribution which does that. Right, so what this is, this will be t less than 1, this is at t equals 1, and this is t greater than 1. That's the value of xt, and that's the probability of xt. And essentially it's peaked around the origin, okay? And at t equals 0, of course, it's actually at the origin. So it's actually a delta spike of height 1 at the origin. And then what happens is for t greater than 0, it becomes a normal distribution, and as t gets bigger, the normal distribution flattens out. What does that mean? It means that at t equals 0, with certainty you can predict where you are, because you know x 0. As soon as you go away from t equals 0, the probability distribution means that you can't predict with certainty where you are, but near to t equals 0, there's a high probability you're going to be close to 0. As t gets bigger, the probability distribution flattens out, the variance gets bigger, so the chances are you're going to be further away from 0 for larger t than you were for smaller t. It's not, you could be close to 0 randomly, but the probability means that you explore more, there's more probability covered by larger values of x, the value of b away from 0. So what that means is that essentially the normal distribution is that the time step, the Brownian motion evolves over time, and you have to stop saying, well, what's the value of the time step at time t? You ask, what's the probability that your Brownian motion is going to be within this region at time t? And as time goes up, that probability in general is going to go down, okay? Because it covers more and more. There's more probability tucked away in the corners. So another thing that you've got here is, because in this particular random walk, you tossed a coin each time you made that random walk, then if the coin tossing was independent, and so was the independent steps between the time steps. So the actual future movements away from a particular position are actually independent of where you are now, so that any distance between some point time in the future and time point now is also going to be independent, and they're binomially distributed, and they also have 0 mean and variance t. That's something that you can show. And then the other thing that shows here is that as these are random numbers, each time you draw a random number, you'll draw it from a slightly different distribution, but that's not so important. Regardless of that, you might draw it from a distribution like here for a certain time t. It'll be a very similar distribution for time t plus dt, but you might get a value down here. So in general, you will have a completely random set of numbers as the height of the binomial walk. And so, in general, they are not going to be, they'll be continuous because you have to walk between the two, but they will not be differentiable. So you have a completely non-smooth distribution curve. The curve is not a nice curve like this that you can draw. It'll be a curve like this. You don't have to take your pen off the paper, but it won't be nice and continuous. So there's that bit of crazy thing is you say, well, hang on, the time step goes to 0, or the jump goes to 0, so surely it must be continuous. No, because what we're doing there is that in the limit this becomes a normal distribution here, and so we're selecting from the normal distribution rather than thinking of having just infinitesimally small jumps. Right, so now, Brownian motion, then I'm going to formally define it. What I've done up until now is I've done it in discrete time. What I now want to do is I want to move into continuous time. Why? Well, continuous time, you can deploy a whole lot more calculus, stochastic calculus on that, and so you can get answers out more easily than discrete time. Of course, computers still work in discrete time. And actually, stock prices will only be quoted in discrete time. So there is a philosophical discussion about what is the difference between continuous time and discrete time. Discrete time is really in the context of what we'll be dealing with the real world, but continuous time is mathematically nicer to deal with. Okay, so we'll deal in continuous time. And yes, there are people that then begin to worry about arbitrage opportunities for going between discrete and continuous time, but we're not going to be so concerned with that here. Right, so in continuous time, I'm going to define standard Brownian motion, or it could be called a Wiener process, and it's going to have a general name B sub t. Generally in stochastic analysis, you don't write B of t like that, you would write B sub t, okay? The t means that it's at that time t, rather than it's necessarily a function of time. It is a function of time, but it's to emphasize that it's only at that instant of time. B sub t has its standard Brownian for t greater than or equal to 0, if and only if it's got independent increments, so that bt minus bs is independent of the history of what the process did up to time s whenever s is less than t. It's got stationary increments in that bt minus bs depends only on t minus s. It's got Gaussian increments in that Bt minus Bs is n naught t minus s. So it's normally distributed with mean 0 and variance t minus s. And t is continuous but not smooth, and B0 is 0. Okay? So Brownian motion came about from a person called Brown in the 1600s who looked at pollen particles on a microscope, under a microscope, and saw that they moved in erratic motion. Okay, and it was essentially because the pollen particles were bouncing off the air particles, which you couldn't see, and so the air molecules, and so it became a random, it looked like a random walk. So after that's why it's called Brownian motion. Okay, so general Brownian motion can refer to something which has a different distribution. Wt minus Ws is normally distributed in that way, but that's general Brownian motion as opposed to standard Brownian motion, which I'm looking at here. So B sub t underpins a lot of what we are now going to use later on. The relationship between standard Brownian motion and other Brownian motions, you can write down these relations. You can write, say, a standard Brownian motion Wt will be the initial value W0 plus a sigma times a standard Brownian motion plus a mean drift term of μt. So mu is maybe a constant, t is time, and that's how much the thing drifts up naturally if there was no randomness going on. So what we can say is that's W0 plus μt. Sigma bt, we can actually say, well, sigma bt is actually sigma root t times n01, because you can rescale it in that way. And then essentially you can add in the mu t to the n01 term there, and using a standard z transform for normal distributions, you get Wt is W0 plus that normal distribution that I've got up there, mu t plus sigma squared t. So you can add together, you can scale standard Brownian motion with values of sigma, you can add mean drift terms on and things like that, and you can end up with something which is still normally distributed, but it's no longer standard Brownian motion, it's just a general Brownian motion. Another thing that is useful, as we'll see later on for when we use martingales, is that it's possible to write a Brownian motion at a future time s in terms of a Brownian motion at time t now, plus the difference between the future and now. So that looks a bit stupid, what I've written there, because clearly if you do expand brackets, you get Bs is Bs, and you think it's Bs. But that's actually okay, you can actually keep that like that, because then there's a distributive property you'll see in a bit in terms of expectations or covariances, which will actually give different values for that on the right-hand side, or it allows you to simplify the right-hand side in terms of the left-hand side. So let's have a look at some covariances here. So if I've got standard Brownian motion, and I ask what's the covariance of the future Brownian motion at time s in the future, given t now, in general that's the minimum value of s t. Well, if s is greater than t, then that's clearly going to be t. But the way that it works is the following. You take the covariance of Bs and Bt, you write that as a covariance of, and that's where you use that formula, Bs plus, or Bt plus Bs minus Bt and Bt. Now, covariances are distributive and they add, so when you do that, you can take the covariance of Bt with Bt, which is there, and then plus the covariance of Bs minus Bt with Bt. Now, covariance of Bt and Bt, well, by definition, that's just the variance of Bt, which is basically given by the fact that it's an n-naught t distribution, so that's just t. The covariance of Bs minus Bt with Bt, well, if that's standard normal distribution, you've assumed that you've got independent increments. Okay? So first property, it's got independent increments, so the future increments are independent of what you've done in the past. So where you go in the future is independent of where you are now, so the covariance has to be 0. So overall, the covariance of Bs and Bt, if it's standard Brownian motion, is just t. Okay? It's a Markov process because it's got independent increments, so you can simulate it using Markov processes if you want to get more complicated. It's also, and this is the first mention of this word, a martingale. Okay, a martingale, what is a martingale? A martingale is something on a horse's bridle, apparently. I don't know why it's called, how we get that in terms of the finance use of it, but the formal definition of a martingale is down here. It basically says if you've got a stochastic process S, in other words, a solution of one of these stochastic differential equations, in other words, a collection, an ensemble of all these paths, a martingale, it says that if there's a measure P associated with it, and don't worry what that means, we'll worry about that later on when we use it, I'm just defining it here. It says that the expectation under some probability measure of a future value of S, given something called the filtration, curly F, up till I, so expectation under P of Sj given the filtration up to I, so this is called a filtration. That's just fancy stats words for history. Okay, so how you got to here, how you got to point I, okay. This is the future value. And this is the current value. So what the martingale probability property says is, if S is a martingale, then if you take if you ask the question, what's the expected future value of this random process, it says that the expectation is just your current value. Sounds a bit stupid. So basically it says that I'm gazing into the future. What is going to be the value of the stock market in the future? Okay? Oh, if it's a martingale, it's the value today. Okay? The expected value is today. What it means is if I ran time an infinite number of times and looked at all the possible values that the stock market took, and then I asked for the mean of all those values, the expectation of those, it will be the same as the value I had today. Okay? Now, the stock market isn't properly a martingale, it's got a mean drift term in it, but essentially this is what martingales are used, why the martingales are useful, because if you can show something is a martingale, and then it's a statistical process, then when you ask for what the expected value is for a future time, it's just the value you already know. So in that sense, they're appealing, because if you can show something as a martingale, the best estimate of what's going to happen in the future is the value that you've got now. Okay? Seems a bit crazy, but there's a lot of use of those, as we'll see later on. So BT is actually a martingale. So standard Brownian motion is a martingale. Why? Well, I'm going to ask for the expectation under some probability measure of a future value BS given the history up until now. Okay, the filtration up until now is F to capital T. So what is that? Well, it's the expectation of, now I'm going to take that same formula as I got up, I'm going to write BS as BT plus brackets BS minus BT. That's still BS, but I've just broken it up like that, given the history up until now. The reason I've broken it up is because expectation is then distributive, so then I put the expectation, I get the expectation of BT given FT, and the expectation of BS minus BT given FT. Right, so the expectation of BT, the value now, given the history up until now, well, the one thing I know is the value now. So the expectation of the value now is the value now. So the expectation of BT is just BT. The expectation of BS minus BT given FT, so the expected value of the jump between now and the future, given the value now, well, if this is standard Brownian motion, it says that we're independent of our history up until now. We've got independent increments, so the expected value of that is 0. So essentially, this turns out that this is the expected value of BS given FT is just BT, which is the same as that formula, which says that that's a martingale. So that follows from the fact that if you want to, you can say that the future distributions BT minus BS go like, or BS minus BT will go like N naught S minus T. So the mean of N naught S minus T is 0. Okay, so when you take the expectation, it's 0. Okay, there's some other scaling properties here. Oh, here's an interesting one. Brownian motion, if you do Brownian motion in 2D, this is the random walk of a drunk home from the pub. Well, that's how it's taught in physics. Okay. So you start at a lamppost or the pub, and then you randomly walk in different directions, all with the same step, and then you ask, well, do you ever get home? Okay. And the answer is, in 2D, you actually will eventually get home. It's possible to show that you will get home. If you do this in 3D, so you can walk up as well as down, and I'll give you an example of what that is in a minute, then you don't always explore. It's just a dimensionality effect that 2D Brownian motion will eventually cover every point on the plane, but 3D Brownian motion won't ever, well, isn't guaranteed to infinite to cover every point on a 3D volume. So this is useful if you're laying mines in the sea, because eventually if you put a mine, an explosive bobbing on the surface of the sea, you'll eventually hit a ship, or a ship will hit it, okay, as it's moving around. If you put the mine floating underwater, okay, you won't necessarily always hit the submarine, because if it's randomly moving around in 3D space, it won't automatically always hit the submarine. But that's a somewhat archaic use of it, because, well, maybe not with the Russians off Cornwall at the moment. But okay, but that's the dimensionality effect. There's a scaling property above, and there's an inversion property as well, which are not so important here. One thing that I want to talk about here is what I mean by dBT is. So I broke down dBT here. This formally is equal to the value at b of t plus dt minus the value of b at t. Okay, and if you look back at the properties of Brownian motion, it says that the increments were distributed like n naught times the time step of the increment. Okay, so what does that mean is it means that formally this is distributed like n of naught t plus dt minus t, so it's normally distributed as n naught dt. So this, whenever you see a dB sub t written there, it means that that is a shorthand for a random number drawn from a normal distribution with mean 0, but variance dt, the infinitesimally small time step. Okay? Right. So, how might we use these to represent stock prices? So Brownian motion by itself isn't going to be enough to represent the stock price. Why is that? Well, Brownian motion, if I set it running, I either go up or I go down. So although I set this at a positive value, there are going to be random walks that end up negative. Okay? Clearly you can't have negative values of stock prices. You have 0 values of stock prices effectively, well that's the lower bound, because when a company goes bust, its stock price goes to 0, it's worthless. It doesn't stop, you don't actually end up owing money as a stockholder. It doesn't work like that, you just end up with no money. Okay, so the share price is bounded below by 0. So Brownian motion by itself isn't going to work. So let's have an exploration of what might work if we want to model stock prices in continuous time. So go back to the first year. If I forget stochastic analysis and I say that the stock price is S sub t, then I might think, well, it goes something like investing money in the bank. Sure. So ds over s is mu dt, say. So that would be like s is money in the bank with an interest rate of mu. Solve that formula, you get s equals s naught e to the mu t. So in continuous time, money in the bank goes up exponentially, or debt goes up exponentially. But we know that we don't have that, but that works in a predictable way. If you tell me what s naught is and what mu is, I can then tell you exactly what the money is worth or stock price is going to be at some point in the future. That's not good either, because we know that stock prices move in a very random way. One model that you can write down for this, and I'll finish here, is something called geometric Brownian motion, which is where you start off with a ds over s is mu dt, which is maybe familiar territory, but then you say, well, so there's a bit of a drift around, there's a bit of a drift up if mu is positive, or a bit of a drift down if mu is negative, but then I'm going to put in this extra random bit here, which is going to be something that accounts for all the unpredictability in the stock price. Okay? So the idea would be is that maybe ds over s is nu dt plus sigma dB, where dB is drawn from a distribution, possibly n naught dt. Right, and we can go on and play with that later on, but we'll leave it there today. Okay? And I'll see you tomorrow, lunchtime, for